Welcome to Module 8 of Geography 660, Applications in GIS. In this module, we're going to be talking about an important aspect of spatial analysis, and that is something broadly known as GIS modeling, which we'll make a shallow dive into. And then we're going to make a slightly deeper dive into an aspect of GIS modeling called cartographic modeling. Really, the module's learning objectives are twofold. The first is to give you a pretty, again, deep dive into cartographic modeling, and I'll also talk a little bit about other types of GIS models, including spatial process models. Trying to outline the lecture here a bit, we're going to start with some conceptual model basics, types of models, some language that you should know about called loose versus tight model coupling that's kind of commonly used in GIS. Then we're going to walk through a number of different basic types of spatial models. Again, the major focus is going to be on cartographic models, and we're going to talk about some of the important steps of those. We'll also expand into more complicated types of modeling you can do within GIS, including simple spatial models and spatial temporal models. I'm also going to give a few editorial comments about modeling in GIS in general. So, one of the key concepts we need to start with, therefore, is what is a model? And in their famous and very influential GIS textbook, Longley et al. Describe models in this manner. Models are expressions of how the world is believed to work. And I really like that definition because it indicates that sometimes our knowledge of how the world works is incomplete. And therefore, any model we make of a process occurring on the Earth or elsewhere may be incomplete or incorrect because it's expressions of how we believe the world to work. And in fact, in a science like geography, people may think the world works in different ways, and there might be two different types of models or different models for the same, trying to explain the same geographic phenomena. So in GIS, focusing down a bit, models are digital or computational, and sometimes you'll hear the term geocomputation used. So we have digital models. In geology, for example, models can sometimes be conceptual, like a cross-section of the Earth describing how we think plates are moving together. I think back to my geology days, I think of all the concepts, all the conceptual models of how the Tibetan Plateau formed, including incomplete knowledge of what's happening to the Indian plate as it underrides Asia. That's a model, it's a conceptual model. In GIS, because GIS is computationally based, we take a model and we implement it in a computational environment. In GIS, models are also spatial. There's many models that you could have that would be aspatial. They don't take geography or place into consideration. Therefore, in GIS, variation in the inputs occurs across space. And processes and equations within the model may vary across space as well. So there's variation across space which is manipulated by the model. And therefore, which is key and probably obvious to people who've worked in GIS, the results of the model will vary when the location of the object changes. So I want to make a few editorial comments about modeling now. First, there's a wide range of complexity that's captured in the term model. And as stated by Longley et al. In their 2005 book as well, model is one of the most overworked terms in the English language, and I agree with that wholeheartedly. I also would like to kind of say the following. Don't let the word model scare you or intimidate you. Many quite useful models are quite simple. And I always like to joke a little bit when graduate students get up saying, "I'm making a model. Oh, I'm really great." And or professors too. And then you really find the model that they're talking about is an empirical relationship between two variables. An example I'll give you, in remote sensing, one commonly measured property is something called the normalized difference vegetation index. And it's been computed for all types of imagery for many, many years, and it's quite important. Well, there's all sorts of models that have been based upon NDVI, including one that kind of relates NDVI to leaf area index. It's quite a useful model, but it's just a function that has related empirical measurements of NDVI to leaf area index. So it's very important, but at the same time it's relatively simple. So don't let the word model always denote in your mind something like a regional climate model or a global climate model, which are complicated beasts, but models can be very simple too. The other question you need to ask is, does the quality or accuracy of my input data justify the complexity of the model used? And there's kind of an acronym, GIGO, garbage in, garbage out. And I'm going to give another little brief example from my graduate days. So I was a graduate student at Cornell, and Cornell had a very strong spatial sciences program at the time. And in fact, one of their faculty, who was not on campus all that much, but was Carl Sagan, which some of you older individuals may know. But spatial sciences, we took a number of classes with these people because there's overlap. And by and large, people going into spatial sciences are typically quite mathematically oriented. You know, think of the gentleman in the Big Bang Theory, for example. So these individuals, when approaching a problem, especially relative to like geomorphologists in geography who might be a little more qualitative and a little less quantitatively focused maybe, would come up with exquisite mathematical models because that's a framework in which they were very comfortable. However, they would be applying these mathematical functions to other planets in the solar system, for which, of course, the input data might be, shall we say, rather limited. So I remember reading a paper that was computing something about Mars to like 6 decimal places. And you're really wondering, that's a wonderful model, but where are you getting any information to feed into the model, and how can you justify the amount of precision that you're reporting your results to? So just things to think about, that you may have a very excellent model and the physics behind the model may be 100% correct, but if you don't have really good input data, the results of that model are going to be questionable, even if it's a perfect representation of the world. So now that I've had my editorial comments on modeling, I'm going to go back to actually why we should model in anyway. So spatial models are useful for a variety of things. They can allow us to describe basic properties of spatial features. That's of interest to some. More importantly, they can describe the relationships between spatial features, or describe the processes that underpin spatial features. Why do we have something in this location and not in another? And help us understand the interactions between things. And I'll show you an example of an interactive model later. They can help us understand spatial forms and behaviors. I'm a geomorphologist by training, and there are GIS models that describe where we find drumlins, for example. That's a landform. And they can, in general, the reason we model is they help us solve spatial problems of interest. So there's a different number of different ways that you can classify spatial models. I've seen a number. This slide uses something from the Bolstead textbook, which is probably as useful as any from an introductory standpoint. And he breaks models into 3 general types: cartographic models, simple spatial models, and then what's increasingly important in GIS is spatial temporal models. Historically, GIS has been very, very poor at dealing with the temporal aspect. This is improving, and models are improving their dealing with time. So in GIS, you can do modeling in a number of ways. The first thing is the approaches that this class has been teaching in GIS, something typically where you go through a process and you do it sort of manually with a mouse and windows using what's called a graphical user interface, or GUI, is maybe not the best way, because in modeling you might have to do something 1,000 times, and you don't really want to be doing that with 1,000 mouse clicks. So really, modeling is done in kind of one of two ways. If you want to you want to do your model entirely within GIS, and by that entirely within a GIS software package, you can do that. And this typically requires a scripting or macro language. Scripting languages are the terms we use today. Macro languages used to be terms that were used in the 1980s, early 1990s. Today, Python is the scripting language of choice for GIS for a variety of reasons. In the old days, ArcView, it was Visual Basic or Avenue. If you really go back to the old ArcInfo days, it was something called AML, which stands for Arc Macro Language. That's doing the model, or creating a model and running a model within a GIS package. Now, that may or may not be an appropriate environment for doing modeling. You can also create a model in an external program like R, IDL, MATLAB, S+, SAS, C++, whatever you want to, and then you can create your inputs in the model using GIS. You run your model, and then you can look at the outputs in GIS. So GIS is a part, but the model itself runs outside of GIS. And these two approaches lead to the following terms. So there's something that's called tight model coupling, and this is when modeling is done within the GIS environment. And in one of the labs for this class, you created a cartographic model using Model Builder. That's a tightly coupled model. It's all done within ArcGIS Pro. Loose modeling is done outside a GIS environment. And again, GIS can be used to prepare the spatial inputs for the model. It can be used to analyze the inputs, and that should have said analyze the outputs. And it can also be used for visualization purposes. Now, we're going to go over cartographic modeling, which is really kind of historic core of complex GIS operations. Now, we use GIS for a lot more things now, but when it was being developed, cartographic modeling was at the heart of GIS analysis. And I have on the left of the screen here a cover from a textbook that describes cartographic modeling. In fact, it's a classic text now. You'll notice if you read this cover that I intentionally selected, it says Mapbox Explorer Diskette Included. For those of you who don't know what a diskette is, it's a little media device that you used to put in your computer. It would store about maybe 1.4 megabytes, and you could store software on there, kind of like key drive today. So just to give you some idea of the dating of this, but a individual we'll talk about in a minute, C. Dana Tomlin, was the individual who's kind of credited with taking the concepts of map overlay created by Ian McHarg, remember that from earlier lectures, and bringing them into a GIS framework called cartographic modeling. And the figure on the right kind of describes this whole idea. And again, you've already created a cartographic model in one of your lab exercises. But the idea is we take a number of different layers or themes about our landscape, like land use, elevation, recreation, and schools. We do some GIS functions on them, like buffering to distances from schools or recreational areas. We might calculate slope areas because we might not want to build on steep slopes. And then what we might do is, in this set, we're doing a reclassification step to making everything kind of comparable, those 3 input layers comparable, or 4 because we're bringing land use into it. And then we weight these with some mathematical function. We combine them to create a surface, just like in map overlay, where some areas are high and possibly great to do something with. Other areas have low values and not so good. That is the idea of cartographic modeling. So this brings a question. What is the basic definition of a cartographic model? Well, going back to Dana Tomlin's 1990 book, a cartographic model is a set of map layers that are all registered with respect to a common cartographic frame of reference. I think you can understand what that means. One thing it should trigger in your mind, if you're trying to do cartographic modeling, everything should be in the same and appropriate map projection. So then what is cartographic modeling? So if a cartographic model is a set of map layers that are registered to a common framework, cartographic modeling is a process of combining these individual GIS layers using GIS analytical operations to create complex models that can solve problems or aid in making a decision, like where to put a new school, for example. Again, I like to think of it as an extension of the map or cartographic overlay process that was pioneered by Ian McHarg, and again brought into the GIS computational framework by C. Dana Tomlin, who is still a professor of GIS and a really interesting character, by the way. Typically, the raster data model is a little bit better than the vector data model for undertaking advanced cartographic modeling. And this is just yet one of many examples of cartographic modeling you can give. This is one that is trying to calculate erosion potential on a watershed basis, and it's from NOAA. And so in this model, a couple different layers were started with: elevation, land cover, and soils, all of which I think you can see how they could contribute to calculating erosion. And then from the elevation data sets, you might calculate slope drainage. And we talked about that in a previous lecture, how you could potentially calculate some of those. From land cover and soils, you could combine to get some estimate of how erodible you think a particular grid cell is. And then if on top of this you throw a precipitation field, you could actually compute the relative erosional potential. And then this is a grid. And then what in this step model builders did was they added a vector overlay in which to aggregate their results of individual raster cells into a unit that is meaningful for people trying to make decisions, and that is a watershed. And so they're using another layer, could be raster or vector, but something to scale up all those individual pixels to a unit that makes sense for decision making. Now, just a word about C. Dana Tomlin, because I think he's an interesting gentleman, and I had the opportunity to attend a 3-day Google workshop with him, and he's really wonderful GIS guru, so to speak. So C, which stands for Charles, but he goes by Dana Tomlin, is the originator of map algebra, and according to Wikipedia, is a vocabulary and conceptual framework for classifying maps to combine map data to produce new maps. One of the things and reasons why C. Dana Tomlin is so important in early GIS was he wrote a couple of software packages back in the day. One is called IMGrid, the other is called MAP. And not only did he make them, but he was open source before the term open source was popular, maybe even been developed. So he made his stuff publicly available to people, and hence his software packages or computer code were incorporated into open source and some commercial software packages, including GRASS, which was developed in the 1980s by the United States Army Corps of Engineers and still exists in open source format today. In fact, the open source movement kind of reinvigorated GRASS. Some of his stuff was built into a image processing system called Imagine, as well as Adrizi, which is a commercial software package that was developed and is still maintained by Clark University, which has a big geography department. And again, his landmark book, Geographic Information Systems and Cartographic Model, have helped lay the foundation for kind of modern cartographic modeling efforts. And in fact, I believe in the last few years, Esri Press has republished this book. That kind of gives some indication of its importance in the field. And I'll give Esri some credit here. They, as a company, have been republishing some seminal works in GIS and cartography that otherwise wouldn't be available to people. So, some caveats about cartographic modeling. So, most cartographic models have historically been temporally static. So the inputs represent spatial features at a fixed point in time, whenever that data was collected. And I think everybody can probably get their mind around that pretty easy. But one of the things you also have to think about in GIS is not every input you have was generated at the exact point in time. And what you may be forced to do is to integrate information that was collected at different times. And in certain areas, like where I am recording this lecture in rural Iowa, where things may not change quickly over time, that may or may not be a problem. I think you can imagine trying to incorporate data that was acquired even maybe 4 or 5 years apart in like a suburb of Houston or Dallas or another part of the world that's expanding rapidly. And taking information from 5 years ago and taking information today may cause problems. The other thing you should be aware of is that cartographic model output is often nominal or ordinal in its geographic measurement scale point of view. So it could be nominal, it could be either suitable or unsuitable, or it could be ordinal, high, medium, or low. It's not necessarily a number that means something in and of itself, like an air temperature. It's typically a nominal or ordinal geographic measurement scale. Just something that's probably obvious, but I'm putting this slide in here just for completeness, is cartographic modeling can be performed in either vector or raster. In the way back history, it was probably performed in one or the other. Today, you can put both data types into the same cartographic model. And here's just an example of a cartographic model, and you've probably seen a number as you've gone through this course. I like this one because it reminds me of some of my friends from my college days who live in some of these areas where these maps are from. But this is an example from the northern suburbs of the Twin Cities, and they're looking where you might want to find places that be suitable for something. So in this simple model, you have a few inputs, lakes, roads, and hydric status, which you use a number of GIS operations. And by the way, the inputs to the model, both the beginning inputs like lakes and roads, as well as intermediate products like the buffers, are shown as boxes. The operation, GIS operations, are shown as ovals. So you can see, you take some inputs, in this case you're buffering or you're recoding, you use overlay to combine them, and finally some more recoding, and you get a suitability ranking where it'd be really great to make your cabin on a lake, which is, of course, the desire of 95% of the people in Minnesota, a cabin on a lake. I'm joking a little bit, but you get the idea. Now, designing a cartographic modeling. So most cartographic models are based on a set of criteria. And like many real-world problems, often they're poorly described or described qualitatively, and it's often the job of a GIS analyst to take this inexact qualitative assessment of a real-world problem you're trying to solve and kind of put some numbers on it in order to combine layers together and solve the problem. So for example, ideally my retirement home in upstate New York would be on a southward facing slope with soils that are well suited to put a septic system on, in part because soils there have some issues, which I could talk about because I'm very familiar with the soils of New York State, but I won't bore you with that. Shouldn't be too far from a road because, of course, if I'm in my retirement dotage, I do not want to be having to shovel huge driveways out. And also needs to have beautiful views of Lake Cayuga. So this would be my problem. And it would be up to some young GIS analyst, because I'm retired, to come up with how you would figure out which inputs you need to answer those questions, what analysis you would like to do. And you would also have to figure out, maybe by talking to me, which of these things is most important. So could I live with a longer driveway? Does it absolutely have to be in the viewshed of Lake Cayuga, or could it be another lake or slightly out of the viewshed? Which of these are important? Because you have to rank which of those are the most important, which are the least important, and you have to come up with a way of being able to combine a viewshed information with slope potentially, or soils and distance from road, in a way that kind of weights them in the way you can understand. And also not only you understand, but you can convey back to the person who you're going to have to bring this decision back to. So what you as a GIS analyst have to do then is to take these criteria and convert them into something that's suitable for a cartographic model, and again prioritize the importance of the individual components. The second thing you have to be concerned about is whether or not there's actually appropriate GIS information in terms of quality and accessibility to you that allows you to create this. You know, there's no reason to include some of these components if you can't even get data that will allow you to address the question. And in fact, if the data is poor quality, it could actually lead you to the wrong conclusion, which would make, in this case, retired Dr. Klein not so happy. So, a few things to consider. We'll talk about rankings and weightings in cartographic models. It is necessary to consider how to create rankings both within a layer, like within a soil layer, which soils, how do I rank soils from being very good for a septic system to very bad for a septic system, and also among criteria. How do I weight soils versus distance from a road? And this is true not only for the original inputs to the model, but for also any intermediate products that come out of one of those operations, which then I have to feed in to yet another step. So for a single input or criterion layer is a good term to think about from a GIS modeling perspective, it's necessary to determine if the layer should be nominal, such as in or out of the floodplain, or soil classes, ordinal, like I could have soil, a good soil, bad soil, or it could be ordinal. This is high permeability for water for septic system, medium or low, or scale it, you know, in the 0 to 10 scale. Or if it's really going to be a continuous interval or ratio values, such as distance from a road. So you need to decide about, for each layer, is it going to be nominal, ordinal, or like interval or ratio, which is the continuous too. So for example, you might have a source layer, and this is an example of changing it from a discrete rank layer, something like an ordinal data set, which is the one that says discrete rank layer, to a continuous rank layer. And in this case, I'm taking the soil types and I'm looking at, in essence, production for crops probably. And in one case, I'm making a nominal layer. If production is less than something, I make it 0. If it's more than something, 1. That produces one layer. Or I could come up with some relationship between production, which in this case is for some really weird reason on the y-axis, and rank to create a 0 to 10 ranking rather than a 0 or 1, it's good or bad. And you can, one of the things you have to think about is how you figure out this relationships between your source data and your final layers that you're going to input into your model. And those are important conceptual discussions that you have to have with yourself or your team that kind of are a little bit outside the technical challenges of making a GIS model. It's also necessary to consider how much relative weight you should place on each input layer. So in my example, for example, is the distance to the road more important than the distance to than the septic system applicability from soil layers? The easiest way to do this conceptually and to actually figure out what things mean in your head is if you can express all the criteria on the same scale. For instance, my distance from the road could be in, from 0 to 1,000 feet. How do I compare that with a soil layer that goes from 0 to 10? Well, you really can't easily. So what you have to do is you want to put everything on the same scale. And one of the most easy ways to do this is to just do a little bit of math, and I can show you some simple approaches that will make your inputs all go from 0 to 1. And again, if you don't do this, it's very necessary to take input values and try to, how do I take a slope value that probably goes from 0 to 20, and most of them are going to be from 0 to 3, and how do I compare that to distance from roads? So it gets really complicated. So put them all on the same scale. And there's different ways to do this. And by the way, the Bolstead textbook has a really good discussion of cartographic modeling. Now, it's not the only approach you can take with these things, but it's certainly a good starting point and is as good as any place to start. One of the easiest things you can do is to linear scale your inputs between 0 and 1, and it's really simple. You simply find the maximum value in your input layer, and then you would subtract every other value from that, and you divide that by the whole total range of values, the minimum by the maximum by the minimum. And that will give you a scaled number that goes from 0 to 1. I highly recommend that. For certain things, you might want to come up with a different scaling, like distance from roads and suitabilities. In this case, the suitability goes up to about 1,000 feet and then drops down. That might become because I don't want to be real close to my neighbors, but I also don't want to be real far from the road. And I could kind of come up with a suitability ranking that would actually hit that sweet spot of, about 1,000 feet. The other thing is I could take a slope layer and come up with suitability. And notice the relationship between slope and suitability in that figure in the lower right there isn't linear. And if you know there's some non-linear relationships, like in this case, lower slopes are much more suitable. Well, small changes in slope at the low end create a bigger change in suitability than changes at the high end. Then you can come up with different mathematical relationships that capture that. But that's a little bit beyond the scope of this class and may be more appropriate to like a GIS modeling class, which you may take later in this program. So finally, what you need to do is, if you have your scaling within your layers and you've scaled them all to the same 0 to 1, for example, then what you need to do is you need to figure out a way to provide a ranking factor or a multiplier that you can multiply each of those layers with that will provide you appropriate weights in your output to the importance of those layers, at least as you conceive their importance. This can be done in really a lot of different ways. One, you can kind of subjectively create some multipliers. Well, I think slope's about 5 times more important than distance to road, so I'm going to multiply all my scaled slope values by 5 and all my distance to roads by 1. That's fine. There are more slightly more sophisticated and eloquent ways to do that. And this slide is from your Bolstead textbook, and rather than take a lot of time trying to walk you through this step by step in this video lecture, I think I will tell you to go work your way through the Bolstead example. It may take a few minutes. It took me at least a couple tries before I got my whole brain around it, but really it's quite simple to conceive. So in this case, we have, I believe we have 6 different criteria, A through F. And what you do is you, maybe in consultation with your team or your client, would rank these. So for example, in this case, criteria D gets a rank of 1, criteria A gets a rank of 4. Okay? And then what you can do is, using the equation provided there on the left, you can take these rankings and you can actually convert them to a weight. And you'll notice that criteria D in this case, which has the highest ranking, ends up with a weight of 0.286, where criteria A, which is 4, ranks up with a weight of 0.143. Now, the key thing about this is, if you look at all the weights and you sum them up, the weights should sum to 1. So this is just one little simple way of going between relative rankings 1 through n and coming up with an appropriate set of weights that, when summed together, sum to 1. And what you can do then is, if you have your different criterion layers, those different layers that should all at this point be through the same range, like 0 to 1, then what you can do is you can take your criterion layer and you can multiply it by that weighting factor. Like, for example, criterion A layer gets multiplied by that 0.148, I believe, weighting from the previous slide, where criterion B gets multiplied by its weighting, and you finally get, you put all of those together and you finally get a suitability number for each cell in that raster grid. And it gives you appropriate weight to each of the layers in respect to their relative importance. And that's one example. I'm just going to put a slide up here. This is something that one of my students and I did in a GIS modeling project years ago, where we were actually looking at the suitability of a particular area of a new city in Egypt called Numinia City, which is near the Nile River, to figure out which areas of this city would be best to build in based on some criteria. And this particular new city suffered from some karst as well as some fracturing of the limestone. And so there might be areas that would be more or less suitable to build. Now, we didn't quite do our cartographic modeling in, our inputs are boxes, our steps are kind of these and not ovals, but trapezoidally looking things. But you can kind of see we can create a model where the end is finally a suitability index. Okay? Notice you'll see some map algebra in there. So this is the cartographic model that enabled us to go from our inputs to creating what areas of this Numinia city would be suitable for development. And one of the things the Egyptians are trying to do actually is, because the Nile River is so important from an agricultural perspective, they're trying to build these new cities outside of agriculturally productive areas so that they're not destroying their agricultural land. And this is my student. He's now an assistant professor at the University of Arkansas. And he's about anything unlike the Muhammad Ali who's more famous. And here's just an example. So this is Numinia City on the eastern desert and the eastern side of the Nile River. There's a kind of a simplified road network, and we excluded agricultural areas because of course you don't want to build where you're trying to preserve agriculture, and we came up with areas of very high, high, moderate, low, and very low suitability. So kind of a classic suitability study, but I just want to give you an example that yes, people do these suitability studies in the real world. So one of the things I'm going to highlight for a few minutes is flow charting. And cartographic models can be presented graphically via flowcharts, which is useful in a few ways. One, it may help you conceptualize what you're trying to do, as well as being able to come up with a graphical way of formally presenting your model to an audience. And I hope that maybe in one of your labs you actually did try this a little bit to put together the flowchart of what you're going to do before you actually try to put it together. I think it's a useful step. And again, if you're trying to use some software like Model Builder within ArcGIS Pro, in essence, you can create a GIS model and the flowchart's right there for you because it's using flowcharting as a mechanism for developing that cartographic model. And here's just an example flowchart which we've kind of seen before, and something that you've already probably come across so far in this course is that one of the things that GIS does is create a huge number of intermediate files or intermediate products, and you really have to keep track of those well, or you just become overwhelmed. But this is a flowchart. Again, boxes represent inputs, ovals represent functions, and it just ties them together. So rectangles again denote data layers, either original or intermediates, and ovals denote operations. So a little step aside, which you may have some experience already in this class, but you'll probably develop more going forward. So there are basically three ways to do spatial analysis or modeling in ArcGIS. One, you can interactively use the geoprocessing toolbars in our toolbox, and you've done that, I think, and that's often how you get started doing things. If you're going to do it once, that's well. You can use the Model Builder graphical user interface, which you've done, and that in fact is much better in ArcGIS Pro than in previous versions of ArcGIS ArcMap. And finally, what you can do is you can actually write your own models using Python programming. And that's beyond really the scope of this class, other than to say you can do it. And there's a little bit in the Getting to Know ArcGIS Pro textbook or manual you can use, but it's really the wave of the future. And a cool thing which I should mention is if you make a cartographic model in Model Builder, it actually is just a graphical user interface way of generating Python code. And you can actually take that Python code and modify it within a Python editor if you want to. So just remember there's three different ways to do it, from kind of the most interactive at the top to the least interactive, but if you're going to make a model and use it many, many times, maybe the most useful is to actually sit down and write some Python code. So you should be all familiar with these geoprocessing tools and toolboxes now. Won't belabor the point, but that's step number one. You should have step number two, Model Builder. And again, you've used this. And I actually, again, find this in ArcGIS Pro really quite useful. And lastly, you can use the Python programming language. And Python is an open source, high-level interpreted language that's quite easy to learn and use. And I highly recommend it because it's now integrated with ArcGIS, ArcGIS Pro, and all sorts of things. The other thing that may not be so useful in the cartographic models we're talking about, but is also a useful tool to do modeling in GIS now, is that there's interfaces between ArcGIS and the R programming language too. So if you really want to know why you should use Python, watch that little video there. And by the way, I use Python for all sorts of things now, both within GIS and outside of GIS. So I want to expand from cartographic models to finish up Module 8, talking about some examples of a variety of complexity when it comes to GIS models in general, to kind of give you some flavor of what you can do in terms of modeling with GIS. We're going to go from the simple to the complicated. So simple spatial models, or as I often like to say, spatialize that. It's a very common approach. Oh, that's the first words on that next slide, say very common. Often there are models of all sorts of processes out there for all sorts of areas. I mean, there's literally, maybe not as Carl Sagan would say, billions and billions, but there are thousands upon thousands of models that we often call point models. And these are models that can be very sophisticated or very simple, that were designed to run at their heart for a single point on the surface of the earth. And one I always think about is when I was a young professor, I was on somebody's committee who was developing a model to predict how much fodder would be available in rangelands in Africa. And there's some very sophisticated point-based models to do this. And you can spatialize these models from a single point to a whole country, which was what this student was trying to do, by simply having variables that vary across space, like how precipitation would change across space, how land use would vary across space. So this is what we call spatializing typically point models. In my own work, there could be models about how much snows on the ground or how much water's in the snow, and I can spatialize these models that were developed initially to run on a single point. The output for these models is often interval or ratio in nature. It's a continuous variable, like how many grams per, or how many kilograms per square meter of area are available for feeding, or how much water is in the snow. Where cartographic models we talked about earlier are often ordinal or nominal in nature. One of the easiest ways to do this is to simply come up with a regression equation, typically based on empirical observations you make, that can relate one field that's hard to measure spatially or with another variable that's easy to measure spatially, or you have continuous surfaces of it. Potentially the easiest example of this, and one this is a really simple example, but there are operational data sets out there that people use in GIS all the time based on this approach. And this is to come up with a relationship, in this case, between air temperature and elevation, because we're only measuring air temperature at a few places on Earth, but we have pretty detailed information about the elevation of the air surface. And what I can do is I can take a relationship I develop based on a few points and extend it spatially based on an LDEM. And this really simple example is simply using the atmospheric lapse rate of 6.5 degrees Celsius per kilometer and giving it a starting value and temperature from fixed location in the upper Rio Grande Valley, and then I can compute the temperature at any other location in the upper Rio Grande Valley. And again, this is a really simple approach, but there are more sophisticated versions of this which are done all the time. And a very good example of this is a PRISM data set that was originally produced by Oregon State University. Another classic example, which as I'm recording this lecture in Iowa is close to my heart because I remember talking about and writing a paper about the universal soil loss equation when I was a high school student in Iowa. And I'm so old, I was talking about the universal soil loss equation. Now it's the revised equation. But this is a really simple spatial model that tries to model erosion in millimeters per year based on a number of factors. A rainfall factor, which you can get from precipitation data, a soil erodibility factor, which you can get from soil survey information about crops, which is provided by USDA, management practices, as well as length and slope, which come from a DEM. And you can put this into this equation and you can come up with an estimate of soil erosion. Now, this is a pretty simple approach. I was talking to a scientist here in Iowa yesterday who says the state is now running a soil erosion model on a daily basis called the Russell model. It's much more sophisticated than this. It's probably one of those we talked about where we're spatializing a point model. But nonetheless, there's this universal soil loss equation, Russell, which you can use. And if you Google this, you'll find many GIS papers on this. And here's just one example of using the universal soil loss equation. Actually, a couple examples. One's from your textbook. The other's from a student who did this at the University of Texas. So you can use this universal soil loss equation based on many different types of data sets, including some examples I've seen from outside the United States where they're getting information about cropping and so forth from satellite images. So an example of a simple spatial model. Another cool example that's actually built in to GIS right now. By built into GIS, I mean there's versions of something in GRASS as well as ArcGIS. But that's to model the distribution of solar radiation on the landscape and how it changes over a year. And these are just an example from an early paper, 1997. I can tell you right now that there are web services that do this. Some students I know created one for the entire state of Minnesota, like on a 1 meter basis or something like this. There are companies that are doing this, and they're all being driven by the fact that people want to put solar panels on their houses. So now you can go and you can look at these solar radiation. They might be kind of more index values for some people because they might not understand watts per meter squared, but you can model the distribution of solar radiation on the landscape, and it can help provide all sorts of useful information for real-world applications. So those are kind of simple. We're going to talk about process-based models, or the power of forward modeling, and notice I have my little E equals MC squared because process-based models are typically based on a number of equations. I've used, over the years, I've had various renditions of this. I decided to pull a real published example to kind of illustrate this. And this is from a paper that came out in 2003 in geomorphology, and it's a comparison of 3 GIS-based models for predicting rockfall runout zones at regional scales in the Alps. And I think this is kind of interesting. So really the idea is you have a problem in mountainous or areas with steep hillsides, is that you may have a source of rocks at high altitudes which may run out and go down and either accumulate at lower altitudes, or from an application perspective can become problematic for roads and other things. And this is just the general characteristics of a slope profile in the Montafon region, and it describes the depositional units which are resulting from these rock falls as well as the source areas. And so it gives you, this conceptual model kind of gives you some ideas. There's a source area at the top. Trees are important because they either slow it down and types of trees matter. So there's all sorts of variables you can consider. And what you try to do is with these process-based models, you try to develop a conceptual idea of the process you're trying to model. And in this case, this illustration kind of gives you an idea of some of the important factors and processes. The other thing, and that I learned from my advisor who was a geophysicist, are you need to start to think about, okay, which processes are important to include, but which processes can I safely exclude without really impacting the quality of my model? And I think sometimes, at least novices, get stuck in the idea, oh, there's all this complexity into the world. But a good GIS modeler can say, okay, yeah, there's all these complications here, but what are the 4 most important factors, and kind of capture those. And if I ignore the 5th, how much is that going to impact my model? So a real strength of creating good process-based modeling is understanding which processes you have to capture and which processes you can ignore. And here's just kind of the 3 models, Rocky 1, Rocky 2, and Rocky 3, which range in complexity. So Rocky 1 only stimulates the sliding of rocks down the hill. Rocky 2 stimulates an initial free fall, so it goes airborne and then it bounces down and then it slides down. And Rocky 3 simulates sequences of bounces and motions. So one would think that Rocky 3 would be the best representation. But if you don't have the processes quite correct mathematically, it could be that a little more simpler model may match the observations a little bit better. So the second step of this process-based is to construct mathematical representations of the conceptual model. And these, in this case, that incorporates the appropriate physics, biomechanics, and by that I mean how do the trees interact with it, so on and so forth, to create a model that's capable of reproducing the real-world process of interest within your GIS. And I couldn't resist, is Rocky 3 the best? And that's something to think about. Maybe the original one's best. Just saying. So remember, the most complicated model may not always be the best. And I think, like I said in this case, somewhat sarcastically, I think Rocky is probably the best. And here's just the flow charts or flow diagrams presenting the models. And you can see how they vary. And again, what drives these process-based modeling are fundamental equations. So this is the fundamental equation in this particular model that has to do with velocity. So the velocity of the rock that's going out of a cell is a function of the velocity going in. Basically the slope and gravity within that pixel, so on and so forth. But the idea is that you have to come up with this process and be able to come up with equations that describe it. The other thing that happens is that often you have to have some coefficients or factors that are adjustable in this. And this is just some studies they've used, and if you look at that equation, there's this mu in there, which is a frictional coefficient. And if you look at it, it has to do with trees, shrubs have different frictions, right? So just an example. And then you can get these model patterns. And I apologize, the grays might not have reproduced very well on this, but what you need to do then is you need to not only run the model, but you need to validate it and go see, well, do my results meet what I see in reality? If they do, you have a good model. If you don't, you don't have a good model. And I'm afraid model validation, while really important, is kind of beyond the scope of this lecture. So those are process-based models. Another really important type of GIS model is a stochastic model, which is based on some element of randomness, and that's why there's the two dice in the lower left. And I'm going to give you an example of this that is a class of model that are called cellular automaton models. And cellular automaton models run on grid cells, grid-based. And this one is an old model that's of interspecific competition for space. And basically, it's looking about invasion of species on a landscape. So you have a grid cell that has some species in it. What is the probability that over time, like the next year, that grid cell is going to have that species in it? Or what's the probability that a new species is going to invade in it? That's the whole point. And that's what the little figure 1 on the bottom right there tries to capture. And basically what this is capturing is for this system that these individual studies, the net rates of invasion calculated from some real-world data. So the arrows will point from invasive species to, you can look at which species is going to invade from another species. So we know the probabilities in essence, or the net rates of invasions for the study area. And the results I'm going to show you were one of my colleagues way back in the 90s when we started at A&M. He ran this and he created a little GIS model of this. And so I'm going to try to make a few points about stochastic modeling from this experiment. So he took the information from that figure there and he built a cellular automaton model. And the idea here is that you have a grid cell, and notice it's looking at the center grid cell as well as the 4 adjacent cells. It doesn't really look at the ones that are only connected at the corners. But what it does is it tries to say, okay, at time 0, I have species 4 in that center cell. Based on the species around that cell, 2 1s, a 3, and a 2, and known abilities of these species to compete with each other, what is going to be the state of that center cell after a year? And we estimate, in essence, what's going to happen at that center cell by looking at the probabilities that one species will replace another one. And that's what the table at the top looks like, where we have the native species, and by native that's the ones that's in the center of the cells, or the center. The invader species are the list of the rows there, and you can come up with a probability that one cell will replace another cell. And in essence, what in this case it's looking like is that if we look at the mathematics for this one particular case, the center cell is species 4. Well, if we look at the table, species 1 has a 0.37% chance of replacing species 4 in any one year, or any one time step. And a time step in this case is a year. And notice that because there's 2 1s next to it, you kind of double that. Species 2 has a smaller probability of replacing that. Species 3 has another probability. Species 5 is not going to have any impact on this particular cell because there's no species 5. And I apologize, I misstated. The other thing you have to do is you have to recognize and take into account that that you have to weight by the number of opportunities. So each one has a 1/4% chance because 1/4 of the boundary is shared. And then you can calculate the probability that the center cell is going to be the same, and it's just 1 minus all those different probabilities of each species moving in. Okay, so it's just a probability approach in the math. What I want you to take away from this is it's all based on probabilities. Just like what's the probability you could win a hand in Las Vegas. And the cool thing about GIS is you can set up different initial conditions. You could have the species randomly distributed on the landscape. That's the one on the left. You could have them aggregated like on a farm field. And then what you can do is you can run an experiment. And in this case, the experiment has many different variables. It has random and aggregated setups on the landscape. It has different amount of barriers, and barriers simply prevent the movement of species into certain cells. You can also vary the proportion of the landscape that is barriers. And finally, you can, because this is a stochastic or a probability model, you have to run it many different times because there's a lot of rolls of the dice in here, and there's a random factor. And what you want to do is you want to run it many times and then kind of look at the aggregate to kind of figure out what's going on, because any particular realization of that world, which is based on random probability, is just one possible outcome. So you want to come up with kind of what does the average outcome kind of look like. One point of this slide is notice that in order to accomplish and look at all these different factors, where we have 2 different types of patterns, 10 different types of barriers, 14 different barrier proportions, and I have to run each one of those things 30 times so I can get kind of an average, you're actually running this whole model 8,400 times to begin to look at what's going on. So it's a lot of runs, and this is why, again, you don't want to use a graphical user interface, because that would be a lot of mouse clicks. I don't have a chance to show you the results. They're kind of interesting. Another model which I was involved in is a more complicated but still probabilistic model based is something called Sleuth that was developed by Keith Clark at the University of California, Santa Barbara, and we used this to simulate the growth of land use in Houston, Galveston, Brazoria. And I'm not sure how easy this is going to show up, but this is the existing land use kind of in the Houston area, where red is urbanized, yellow agriculture, green forests, so on and so forth. And what you can do is, hopefully this will work, is you can model over time the expansion of the Houston metropolitan area. And notice as I go these different time steps, you'll see the growth of Houston. Again, there's what it is at the start of the model. Oops. And we can go back, go through again. Notice how it's growing. And this is like 20. I can't remember the times, but it grows, which isn't surprising. And this is based on cellular automata rules. Really, one of the future tracks of modeling in GIS is something called agent-based modeling. And these are kind of object-oriented models where you have agents or agents that move around the digital landscape, and they interact with the environment. Then they can also interact with themselves according to pre-specified rules that you set up. And one thing I would like to say is what people are finding when running these agent-based models is that you can get very complicated behaviors that can emerge from a relatively simple set of rules that describe the interaction of these agents. These agents could be people walking through airport terminal. These could be agents that could be people who are interacting economically in different ways in an area. But we really get really interesting and complicated behaviors that kind of mimic what we see in reality, and they're actually based on relatively simple rules of how these agents interact with each other. There's 3 links here of some simple GIS models that you can watch, and I'll turn you over to those to watch if you wish. I just really want to point out that agent-based modeling is really kind of one of the future directions GIS modeling is moving. But process and stochastic models will still be of use. And the simple cartographic model that we spent the most time talking about over the course of this lecture remains important for using GIS to solve many real-world applications. I hope you've enjoyed this lecture.